So in this video, we're going to be doing the exercise question. Okay, so the first question says that what is the force between two small charged spheres having charges of 2 into 10 raised to minus 7? Okay, so we're doing 1.1 exercise 1.1 of your reader, and the first question is we have given that q1 is equal to 2 into 10 raised to minus 7 coulomb, right? And q2 is also given, that is 3 into 10 raised to minus 7 coulomb, right? Placed 30 centimeters apart in air. R is equal to 30 centimeter, right? Now, simple basic formula that we have learned is F is equal to K Q1 Q2 by R square, right? And this 30 centimeter should be converted to meter, so it will be 30 into 10 raised to minus 2, right? 30 into 10 raised to minus 2. That is because we have to convert to meter. Now, what is the value of K? 9 into 10 raised to 9 into Q1 is 2 into 10 raised to minus 7. This is basic substitution, and after you substitute your values, you'll get something like this. The thing is, the calculation part is a bit tricky. It's always tricky in physics, but then what we're going to do is we're going to take all your 10 factors, 10 value digits, all of these, we're going to take it in one, 10 raised to 9, and you already know how to do the exponent stuff. So we're going to solve all the 10 10 to the power and these exponents first, and then we can do these rest, right? So we'll have this left, that is 2 15s are, 3 5s are 15 over 3, 3 5s are 15, and then we have, what else can be cut? Yeah, that's it, I guess. Yeah, so 5 then plus 3 minus 2, right? Minus 2, so we get this as minus 2, and then we can write it as 6 into 10 raised to minus 2. But then what we are doing is we're multiplying with 10. What we're doing over here is we're shifting this, right? Over here we have to shift, so it will become 6 into 10 raised to minus 3, right? So this will be your final answer. And now this is force is what? A vector quantity. So if it is a vector quantity, what will happen is this force, you should write its nature, whether it is repulsive or attractive. This you have to write, or you have to write the directions. That is along which direction, along the diagonal, along the right, along the left, or along the BC, AC, whatever that is given. So right now we have no force direction that is given to us, that is along the diagonal. We don't have any figure with us. So what we're going to use is its nature, that you have to mention. So the nature will be, first look at these values, it's plus and this is also plus. So basically it's saying that you have 2 plus q charges. That means it will attract or repel. Okay, so these are like charges, and like charges, as you know, they will repel. So your answer will be repulsive, right? Your answer will be repulsive. So 6 into 10 raised to minus 3 newtons, repulsive. The nature will be repulsive. So this is your final answer. Alright, so this is how you solve the questions, numerical. This was the most easiest one. You just have to substitute the values and do the calculation. So this was a bit detailed, so that like I wanted to show you how the numericals are supposed to be done for the substitution last. So let's move on to the next one, which is 1.2, and this is also related to force. And you may open and read the question yourself. So the electrostatic force on a small sphere of charge. Okay, so you have a small sphere of charge. So Q is equal to 0.4 nu c due to sphere of charge 0.4 nu c due to another small sphere. So we have one small sphere and another small sphere. So this is of charge Q1 and this is of charge Q2. And Q2 over here, Q2 is given as 0.8. The electrostatic force is 0.2 Newton. That means we have given as F is equal to 0.2 Newton. We already have force given. That means what is the distance between the two spheres? That means we have to find R square. We have to find R square, or basically R, right? Alright, so we have these given values, and now let's just try to find the answer. It's pretty simple, right? We already got to know the idea what we have to find and stuff. So let's find F is equal to K Q1 Q2 by R square, and let's substitute the values. That is 0.2 is equal to K is 9 into 10 raised to 9 into 0.4. Now over here we have this new quantity, this with 10 raised to minus 6. Same for this value, so we're gonna multiply 0.8 into 10 raised to minus 6. Okay, and we have to find R square. So I'm just going to send this value over here, R square 0.2. Now we can solve this, and no idea why. And then this square will go here, and then it will become 10 raised to minus. So we basically have 12 centimeters. Alright, so check the ratio. KE square by GMEMP is dimensionless. So check that whether this is dimensionless. That means if it does not have any dimensions, look up a table of physical constants and determine the value of this ratio. So we have to determine this ratio's value, and what does this signify? So how we're going to solve is this: the gravitational constant, and its value is Newton meter square per kg square, right? We already know this, and if you don't know, you can find it out by using F is equal to G m1 m2 by R square, where you can find G value from here. So we have these, we know already, right? We already know this, and then what else do we know? M and M, right? So that is basically mass. So what we can write here is G value Newton meter square per kg square into mass, that means meter square. I mean, I think it's mass square, right? Kg square, my bad. Most probably. Yeah, so it's kg square, right? And E is the electric charge, which is coulomb, right? So we have C square over here. And K, if you know, it is your constant. That is, again, F is equal to K Q1 Q2 by R square, right? And K value, you can see it is F R square by Q1 Q2, right? Is your K. Now Newton meter square Coulomb square. So we have this as well, Newton meter square Coulomb square. Okay, so this is what you get, right? Now you can see that this Newton meter square cancels, and what else can be cancelled? Yeah, so this C square is over here, Coulomb square is over here, right? So Coulomb square cancels, so this will be what? 1. And then we can see kg square cancels, so that means it is dimensionless. I mean, it has no units, right? No units. So given ratio is dimensionless, that is m0, l0 and t0. Next one, explain the meaning and the statement of electric charge of a body is quantized. That means you have to explain whether the body is quantized or not. And why can one or ignore quantization of electric charge when dealing with macroscopic, that means large scale charges. So the electric charge of the body is quantized, means that only integral numbers of electrons can be transferred from one body to another. You can see Q is equal to plus, minus, n and a, right? So over here, n value cannot be equal to any whole number, or cannot be equal to any fractional number, or like it can only be any integral number. That means 1, 2, 3, 4 till n. Okay, can be transferred from and it can be plus or minus. That also we saw. And it can only be transferred from one body to another. Charges cannot get transferred in fractions. Hence, the total charge possessed by a body is only in integral multiples of the electric charge. That means it can be only 1, 2, 3, 4, 5, 6, 7, like that. In the case of large scale or macroscopic charges, the charge which is used over there is comparatively too huge to the magnitude of the electric charge. That means on macroscopic level, the quantization of charge is of no use. That means when, for example, you're taking some small microscopic level, that means we're calculating Q1 and Q2, right? We're calculating Q1 and Q2. That is a small charge. Now, what if you're taking an electric wire? That is, this is your electric wire. In your household, you use electric wires, right? Now, in these electric wires, it's pretty huge, and there will be so many charges, right? N number of charges. That means like many of the charges. You can't be calculating single charges for like 1.6, whatever the charge is. You can't calculate that. It's practically impossible. That means quantization is not like, it is ignored. We can't use that. We have some other formulas and stuff to do that. Okay, we have those integration and stuff. But right now what we're doing is we're calculating Q1, Q2, and we're finding force on that electrostatic force, right? But on the macroscopic level, we can't find that. So that means on macroscopic level, the quantization of charge is of no use, and that's why it's ignored. All right, electric charge is considered to be continuous. That is on macroscopic. Okay, so the next one is when a glass rod is rubbed with a silk cloth. That means when a glass rod is rubbed with a silk cloth, charges appear on both. That means, like, for example, when you do those activities and you test your, like, with a balloon, right? You take a balloon and then you rub it on your hair. So there is some charge that is produced, right? That's why your hair starts like flying or something. But yeah, a similar phenomenon is observed with many other pairs of bodies. Explain how this observation is consistent with the law of conservation of charge. So there's some theory stuff that we have to just read and like understand. When two bodies are rubbed against each other, a charge is developed on both the bodies. That means when any two bodies are rubbed with each other, there is a charge that is getting produced, right? A charge that is getting produced. These charges are equal but opposite in nature. That means they are equal and opposite in nature. And this phenomenon of including a charge is called charging by friction. That means between these bodies, you get a property called friction, right? You can, obviously, friction will come into play. So the net charge on both the bodies is 0. Net charge is basically 0, and the reason behind that is that equal amount of charges repels it. That means if you're putting like this is the silk cloth, for example. This is your silk cloth and this is your glass rod, right? So when you're rubbing against each other, there is equal and opposite opposite like the charges are equal and opposite, right? And then there is like this friction as well, and then what else? We can see that the net charge on the bodies is 0 because there is like, for example, if this body is putting a force F, this body is also putting another force F, so it's basically net charge is 0, right? So when we rub a glass rod with a silk cloth, charge with opposite magnitude is generated over there, and this phenomenon is consistent with the law of conservation of energy. A similar phenomenon is observed with many other pairs of bodies. Next is another one, that is 4-point charges, this, and they're placed in a center of a square. What happens? So we'll do this. Alright, so the question says that there are 4 bodies, 4-point charges, okay? So we'll draw the figure. So this is your question, alright? And now what we have to find that, what is the force on the charge of 1 microcoulomb placed at the center of the square? That means we have to basically calculate the force of the charge over here in the center of the square. How will we calculate that? It's very simple. For the first step, the first very important step is you have to know how to mark the directions of the force. This is what you're going to do in all the numericals of the force. Direction of force. And I'm going to teach you that right now. So, listen carefully. Here, over here, see. Alright, this is QA, right? And this is O. So, we're going to look at only these two charges. Force on O, right? We need to find force on O. So, force on O due to A. Okay, force on O due to A. This is positive, this is positive. Like charges repel. That means it cannot go over here, right? Because it's attracting. So it will go away from A. So we'll mark it over here, away from A. That is force on O due to A. Alright. Next we move on to B. So B and O. Let's look at B and O. It's -5 and this is 1, right? This is 1 and that is -5. So we have unlike charges. Unlike charges will attract, right? Unlike charges will attract. So what will happen? It will attract, right? But right now we're looking at force on O, right? So this will attract. So you can see this, that they are basically attracting. So force on O due to B. Alright, these are attracting. So this charge will go on the side of B. So it will go towards B. Alright. Now next is C. Let's see C. So C and O. Look at C and O. Over here you can see that this is plus and this is plus as well. So you can see that they are like charges and they will repel. So it will go away from C. So away from C means this direction. That is force on O due to C, right? So how you write it? Force on O. We're finding out O. So force on O due to which charge? C charge. Next we move on to D. You can see D, that this is minus and this is plus. So you probably have gotten an idea that it is unlike charges, and unlike charges will attract. That means it will go on the side of D. That means it will go towards D. That is force on O due to D. Alright, so this is how you mark the directions. Now let us find the magnitudes. So your second step will come, which is magnitude of the charges. That's what you do in the second step. So let us find the magnitude of each charge. So first let's find magnitude of force on O due to A. K Q1 Q2 R square. Alright. Now, what is K? 9 into 10 raised to 9 into Q1 is, what is Q1 over here? On A, right? So Q1 is 2 into 10 raised to minus 6 because it's microcoulomb, and then 1 into 10 raised to minus 6. Alright, this is how you find it. Now, R square, here comes the twist, that R square. You have to be very thorough with the concept. R square is what? This is your O, right? This part. So your R square is basically this value, this one, and this one. It is not this value. It is not that one. We're saying R square means these values. So for this, you need to calculate what is R from here, right? We have R given as 10 from this value. So like we know that this is 10. So what will be this? Basically, you have to just remember this formula, that from the center of a square to the vertices, the value will be side by root 2. Alright, so this will be side by root 2. This will be side by root 2. And then this part will also be side by root 2. And this will be side by root 2. So this is your formula. So from the center of a square to the vertices, we have length R will be side by root 2. Okay, so we're going to use that over here. That is side by root 2. Side is what? Side is 10 by root 2, the whole square. This is how you find it. Now you just have to calculate. Alright, you get this value. Now over here you can see we got the value. Okay, but see, I'll tell you one thing. First we'll find FOB as well. Okay, so let's find FOB. K Q1 Q2 by R square. That is 9 into 10 raised to 9 into Q1. Q1, what is Q1? Q1 is B, right? So 5. Alright, over here, why did we take 5? Because we are finding only magnitudes. In vectors, we cannot take these minus and all sign, because these minus indicates the direction. Minus and plus indicates the direction of the number, whatever, right? But we're using vectors, right? So in vector addition or whatever we're using, like the vector quantities, we are not supposed to use the minus sign. That means we'll just take the magnitude, that is the number. So we'll just write over here 5, okay? And then 1 into 10 raised to minus 6 into 10 raised to minus 6 by 10 by root 2 square. Okay? Or FOC, when you find FOC, you'll get 9 into 10 raised to 9 into 2 into 1 into 10 raised to minus 6 into 10 raised to minus 6, and then we'll get the same answer. So you see over here that we get the same answer for this, like we get this answer same as this one. Okay? That is 3.6 into 10 raised to minus 6. And you can see that this answer will be same as the other one that we're going to find, which is FOD. FOD, if you find, it will be 10 into 10 raised to minus 9 into 5 into 10 raised to minus 6 into 10 raised to minus 6 and 10 by root 2, the whole square. Okay, so you can see that FOD is same as FOB. What can you notice over here? You can see that these lines, I'll show you, this line and this line is equal and opposite. This line and this line is equal and opposite. That means they will cancel each other. So the third step that we're going to do is, after finding magnitude, we need to find the force, resultant force. So let's find resultant force. How do you find resultant force? This is equal and opposite. That means it will get cancelled. The answer will simply be 0. But in vector addition, when these are equal and opposite, or it is opposite basically, if suppose this is 5 and this is 2, okay, this is 5 and this is 2. So what will happen is we're going to subtract 5 minus 2. That will be 3. Alright. That's how you do it. So the resultant force will be along the, obviously, the bigger direction. That means it will be like this. So we're just going to subtract. Suppose if it is in the same direction, this is 5, this is 2, we're going to add them. That is 5, 7, right? What if it is with an angle? So for example, the vectors are making an angle theta. So we're going to find resultant force is equal to root of a square plus b square plus 2ab cos theta. That's how you find it. For example, yeah, we'll solve question, right? So this will be f1 force plus f2 square force plus 2f1 f2 cos theta, and the angle will be given. Okay, so that's how you find resultant vectors. So right now you can see that they are in the opposite direction, so we're going to take FOC and FOA. So FOC and FOA, it is equal and opposite. That means FOC is equal to FOA, and we're going to subtract it, FOC minus FOA, which will get 0 Newton. Then same you can see that FOD and FOB are equal and opposite, so we can subtract them as well. So FOD minus FOB, you get 0 Newton. All right. Also, one more important thing that you have to remember is when you're marking the magnitude, when you're finding the magnitude of the charges, you need to mention direction as well for all of them. The direction you have to mention, you can tell the direction is, where is FOB? FOB. FOB is along, acha, this is FOB, right? FOB is along OB. FOB is along OB. And FOA is along AO, right? FOA is along AC. That means AC. That's AC, right? A, B, C, D. So basically the directions, I literally told you how to find the directions, right? I'll just show you again. This was FO. So FOB, OB, right? FOB was along OB only, right? FOB was along OB, right? Then done. FOA means FO and this A was along. FOA is what? It's opposite. So you're gonna say it's along AC, along AC. That's it. Then FOC. What is FOC along? Along CA, right? It's CA. That means it's along CA. Or F. Okay. Then after that, FOD. FOD is attracting force. That means it's along OD, right? You can just see the direction. It's not a big deal. So that's it. This was the question, and basically the forces were equal and opposite. That means you can just write FOB was equal and opposite to FOD, F vector. Okay, remember to write vectors. So it's like that. All right. Now let's move on to the next question. 1.7. That is, an electrostatic field line is a continuous curve, right? It's a continuous curve. That is, a field line cannot have sudden breaks. Why not? Because when a charge is placed in an electrostatic field, it experiences a continuous force. Therefore, an electrostatic field line is a continuous curve, and the charge moves continuously and does not jump from one point to another. So the field cannot have a sudden break. Now, why two field lines can never cross at each other at any point? Because when it crosses, see, we already learned this in magnetic chapter as well, right? That last 10th grade. If you, for example, it's going like this. At one point, you can have two tangents, right? And the direction will be showing two directions, which is not possible. That means if two field lines will cross each other, suppose field lines are crossing each other, you'll have two tangents. That means two directions at the same point. That means at the same point, you're finding two directions. That is not possible. Okay. Next is 2-point charges QA and QB are located 20 centimeter apart. That means we have R value, we have Q1 value, Q2 value. And what is the electric field at the midpoint of O on the line AB joining the two charges? That means this is your AB, Q1, Q2, we have charges, point charges, and what is the midpoint? So this is O, okay, 20 centimeter. That means this is 10 and this is 10. Okay, two charges. What is the electric field? That means we need to find the electric field. Okay, electric field formula we have to use, that is KQ by R square. So what is the electric field? Alright, so what we have to find over here is electric field at midpoint O. Alright, simple, very simple actually. We have to first find directions, right? So let's find directions. Direction on this, let's take this one and this one. So Q1 is given as 3 nu c, and QB is given as minus 3. Okay, so O is, so we have to find, right? So this is minus, this is plus, and we know that electric field directions is marked. If it is negative, we have to go like towards negative, and if it is positive, you have to go away from positive. That means electric field directions is positive, so you have to go away from positive, and if it is negative, you have to go towards negative. Okay, just remember this part. So just tell me where it will be. This is, we don't know, right? We don't know the charge, but we don't know, we know that this is positive, so we'll go away from positive. So this will be your E. Okay, E1. Okay, we'll just take E1, and E2 will go, this is negative, it'll go towards negative, right? So we'll mark this E2, it's going towards negative. Now what happens over here, you can see that it's adding, like it's on the same side, so we'll add the resultant magnitudes. Okay, so we'll just add E1 and E2, we'll get the answer. Okay, so we're going to add them. Okay, that is basically E1 plus E2. All right, so let's add. So E1 plus E2 will give you a magnetic field of E at point O, right? E net, whatever. So let's add E1, K, Q1, Q2. Okay, so see, E1 and E2 have same charges, that is 3, minus 3 and plus 3, right? But then we're going to take the magnitude, so it's 3. That means it is both, they are both equal. So we're just going to multiply it, right? K, Q1, Q2 by R square, right? We can just multiply. That will be 2 into 10 raised to 9 into 9. This is K, and then Q1 is 3. Q2 is, sorry, my bad. K, Q1, right? K1 kq1 by r square, and then we have r square, that is 0.1 the whole square. 6 9 54 into 10 raised to basically 5.4 into 10 raised to 6 Newton per coulomb. Now this is a vector quantity, so we have to find direction as well, and the direction will be along positive to negative, right? See, it'll always be along from positive to negative because it's going to be away from positive, so it'll be positive negative, right? You already saw it's over here, right? And the charges were acting like both of them were over here, so it's going from positive to negative. So write positive to negative. That's it. Okay, so the next one is, if a negative charge of magnitude 1 point whatever is placed at this point, what is the force experienced by the test charge? That means that, see, this is the same figure, right? And the second part of the question, where is the second part? If a test charge with potential of this q is placed at the midpoint O, that means this is your q1, this is your q, and this is your q2, right? This is your O. And if you have 1.5 into 10 raised to minus 9 coulomb right over here, let the force, let's say let the force be F is equal to QE, right? F is equal to QE. So the force on the test charge is QE. It's given by QE. It's the formula, right? So basically, what is this Q? It is 1.5 into 10 raised to minus 9, and E we already found, right? Which is 5.4 into 10 raised to 1. So the force will be basically multiplying these both. That will be Q is 1.5 into 10 raised to minus 9 into 5.4 into 10 raised to 6. Okay, so you just have to multiply it and you'll get the answer as 8.1 into 10 raised to minus 3 Newton. The force is directly along OA because the negative test charge is towards blah blah blah. So the answer is basically that it's going, see, I'll show you the directions. This is Q1, Q2, Q3. Okay, this is your center O, and this is your positive charge, this is your positive charge, and this is your negative charge. So basically first it was going over here in this direction, right? At this direction, EOA was going in this direction away, and EOB was also going in the same direction. And then what happened was that your F vector, like your F vector is minus 1.5 into 10 raised to minus 9. It is given that it is minus, what's the question? If a negative test charge, right? A negative test charge, that means it is minus over here. So we have to put it as minus. That means it's going in the opposite direction. So it's going to go from negative to positive. It's going to go like this, right? See, this is negative. So F vector is going in the opposite direction right now. Negative to positive. Okay. See, we can see it is force, right? Listen, force. To find the direction, why are we using negative to positive? Why is it not like this? Why is it only like that? So the direction I'll tell you. Force, right? So see, it's a force. So force, like charges will repel. So this is minus, and this is also minus. So they won't attract, they will repel. So it will go over here, right? And these and this will attract. So it's that's why. This is minus, this is minus. Minus will attract to repel. So it will go in this direction, right? So this is from negative, direction will be from negative to positive. Alright, that's it. Along OA. Next question is, a system has two charges QA and QB located at points A, B respectively. What is the total charge and electric dipole moment of the system? So we have to find electric dipole, okay? Electric dipole P is equal to, which I will use a formula later. Two charges are given, point A, point B. Right now we need to find what is where is it located in the coordinate system. You can see that this and this X and Y is 0. That means it's located in the Z coordinate, right? So it is like this, like it's going like outward, right? So Z coordinates basically. So we got to know that it's in the Z coordinates. And if you see the total distance R is 15 plus 15, right? You're not going to take the minus signs. So 15 plus 15 is, that means your whole line, this is from here to here it's 15, and from here to here it's 15, right? So this total will be 30 centimeter, right? Okay, now you can see that this is your Z, and then this is also your Z coordinate. Okay, so at point A total charge is, and at point B you have this charge. Total charge system will be QA plus QB, that is 0. You'll get a 0, right? Because it's the same thing, right? Minus. Distance between two charges at point A and B, distance will be 30 centimeter, that is 0.3 meter. Dipole moment of the system is given by P is equal to QA into D. What is that? Okay, see, P is equal to 2A P vector Q. That means 2AQ, alright? So 2A is basically what? A is your 15, right? A is 15. So 2A will be 30. 2A will be 30. So 30 into 2.5 into 10 raised to minus 7. That is 30 into 2.5 into 10 raised to minus 7 is equal to into 0.3, right? 0.3 because there is meter. So the answer will be 7.5, right? Along positive Z axis. Why positive? Because you can see that this is 15 and this is 15. Now the thing is QB is minus and QA is plus. So electric dipole goes from the negative to positive always. It goes from the negative to positive. That means it goes from B to A. All right, positive side of z-axis. We can just write along B to A, or what is B to A basically? B to A is the positive or negative side. That's a wait. Therefore, the electric dipole is along positive z-axis. That means B to A.